The evolution to trajectory-based operations, or TBO, is in progress across the NAS. TBO introduces a fundamental shift in air traffic management and expands the use of time-based management, TBM, a process for assigning and managing times of specific flights at key constraint points to create and manage an integrated schedule. TBO enables all systems and stakeholders to have a common understanding of aircraft trajectories, helps reduce reactive decision-making, and the use of static miles and trail restrictions. TBO success depends on two things: technology and people. Technology. This video explains the time-based flow management, or TBFM system's scheduling and metering tools in support of TBM of air traffic flows. The system is customizable to provide for the local environment as it supports air traffic controllers and traffic management personnel with managing arrivals to an airport. TBFM design addresses available airspace, airport configuration, fleet mix, weather conditions, route structure, typical flows, location of merge and constraint points, and flow-specific spacing between aircraft that is consistent with operating conditions too. Site-specific adaptation is necessary to ensure accuracy of TBFM predictions and the overall stability and reliability of the schedule that it generates. While performance-based navigation, or PBN, capabilities on board aircraft are not necessary for TBFM to work well, they do provide a higher level of precision in adhering to the PBN routes and procedures. As such, they help improve accuracy and stability of TBFM predictions and schedules, and overall efficiency of traffic flow management. People. The facilities that manage the arrival traffic flow, the TRACON, the Host Air Route Traffic Control Center, and adjacent centers, form an operating area. Each facility within an operating area has needs and expectations for traffic management, but they must work together to deliver efficient arrival flows. TBFM design and adaptation ensure that workload is allocated appropriately across facilities into manageable delay allocations for each sector. This ensures the intended schedule is feasible and that delays can generally be absorbed through minor adjustments to the trajectory, such as speed adjustments or small vectoring maneuvers. Because air traffic management personnel need options and flexibility to help maintain a balanced workload, the TBFM adaptation in each arrival system is flexible and designed to balance the right amount of structure, which provides a predictable schedule, while leaving enough flexibility to allow options for responding to operational conditions as they arise. The FAA is implementing a robust change management strategy to help prepare the workforce for the operational changes that TBO will bring. This includes leadership mobilization, consistent communication and coordination, integrated evolution planning, training, and alignment of processes and procedures. Atlanta International Airport is the focal airport of the Mid-Atlantic operating area and one of the busiest airports in the world. The Atlanta airport was built with efficiency in mind. Its 5 east-west oriented runways are aligned with prevailing winds and spaced wide enough to allow triple simultaneous instrument landing systems, or ILSs, in either direction, even in low IFR conditions. Located centrally in the Atlanta center, the airport is somewhat isolated from other busy airports and enjoys relatively stable weather patterns. All of these factors help the Atlanta Traffic Management Unit, or TMU, establish routine use of TBFM as an integral part of its arrival management strategy. TBFM design for Atlanta evolved with use and increased experience with the TBFM system and airspace design improvements such as Metroplex. TBFM design for Atlanta supports heavier traffic flows from the north with dual arrival streams and fixes, and lighter flows from the south with single streams and fixes. The design also accommodates optimal profile descents that start at TRACON boundary rather than top of descent. TBFM freeze horizons are further away from Atlanta than typical to stabilize flows and provide flexibility with adjusting runway assignments, especially during periods when arrival rates decrease as individual runways transition from VFR to IFR. Also, Atlanta's TBFM design considers route structure in the adjacent centers and capitalizes on the ability of the adjacent centers to consistently accommodate the needs of Atlanta. Therefore, adjacent center metering, or ACM, remains the right tool for managing traffic flows to the TRACON boundary, while still providing sufficient opportunity inside terminal airspace for any runway reassignments that may be needed. Atlanta Center seamlessly transitions in and out of metering operations when needed, with all of the adjacent centers, ZME, ZID, ZHU, and ZJX. The only exception is ZDC, which transitions from metering to miles in trail with enhanced departure capability, or EDC, departure scheduling. ZDC does not meter to Atlanta because of the long distance from the center boundary. Instead, it relies on scheduling its departures into EDC. Additionally, ZBW and ZNY centers also schedule to Atlanta timeline. Atlanta's successful use of adjacent center metering and departure scheduling in support of arrival metering operations has paved the way for introduction of more advanced TBFM capabilities throughout the NAS, such as IDAC and TBFM to TBFM or T2T data sharing. Denver International Airport is the focal airport of the Northwest Mountain Operating Area. Terrain and weather create unique challenges for management of arrivals to Denver. The airport sits in a bowl-shaped depression 30 miles east of the Front Range, a line of mountains running north and south, and the beginning of the Rocky Mountains to the west. As prevailing winds fall off of the mountain range and swirl into the bowl, it creates dynamic and volatile weather phenomena that are difficult to forecast and react to. Denver deals with wind shear, microbursts, gust fronts, virga, and other rapidly changing meteorological conditions on a daily basis. Even with 6 runways, oriented north, south, east, and west, over 24 possible configurations to choose from, the task is challenging. There are regular occurrences of tailwinds to every runway at the same time. Combined with that, the dry air and high altitude, field elevation is around 5,500 MSL, means traffic is flying faster in the pattern and on final than at most other busy airports. Even demand is unique at Denver. Extremely heavy traffic from the east alternates with heavy traffic from the west and necessitates frequent changes in airport configuration. Between the concentrated peaks in demand and quickly changing atmospheric conditions, balancing structure and flexibility is a delicate dance at Denver. Denver TRACON and Center dynamically balance air traffic flows and adjust their actions throughout each day, which means they need options. Denver arrival system was designed with this in mind. The design included dual arrival procedures on all 4 corners to accommodate high volume coming in waves from different directions. The route structure extends into the adjacent centers. The metering arcs were designed to allow flights to be captured from many directions as traffic flows are adjusted. TBFM adaptation for Denver provides 29 configurations to allow Denver facilities flexible options for flow management. Like Atlanta, Denver TRACON is somewhat isolated from other major airports and needs to distribute some delay to adjacent centers in order to provide even delayed distribution and keep flights on the desired routes with only speed adjustments and minimal vectoring. The ACM capabilities provided insufficient flexibility to handle the dynamic changes in Denver traffic flows. An extended metering or XM design, on the other hand, provides ZDV TMCs more flexibility by moving arrival systems' freeze horizons closer to Denver and by adding another set of constraint points, or XMPs, and freeze horizons further out into the adjacent center's airspace. This creates a buffer zone where arrival schedules can be managed with greater flexibility to absorb large dynamic changes in traffic flows in ZDV and the surrounding centers, ZKC, ZMP, ZLC, and ZAB. Each adjacent center manages its own XM timelines within the Denver TBFM system. Delay data from the Denver arrival system is incorporated in the XM system and is purposely built for arrival flows into ZDV. ZDV is in constant communication with D01, adjusting and coordinating changes with the adjacent centers. They in turn react and adjust, allowing ZDV to catch the wide variety of traffic, blending and merging and finally delivering to the TRACON. This XM design also expands the options in the ZDV TMU toolkit. It allows the use of XM in more stable times, single-site metering, where adjacent centers provide MIT with EDC and ZDV meters internally, hybrid metering, where the adjacent centers meter to ZDV while ZDV provides MIT to Denver TRACON, or full-scale MIT with departure scheduling into en route departure capability and arrival system. The TBFM design for Denver ensures that delay could be distributed en route and then delivered to the TRACON with enough predictability to keep more flights on their procedures. The Los Angeles International Airport, or LAX, is the focal airport in the Southwest operating area. However, the Harry Reid International Airport in Las Vegas, or LAS, plays an integral role in the dynamics of the operating area. Similar to Denver, Las Vegas experiences several peaks in traffic each day. However, Las Vegas has fewer runways and airport configurations and relies on adjustments in arrival rates in anticipation of alternating departure and arrival peaks. Geographically, military airspace and mountainous terrain surrounding Las Vegas creates a rigid route structure that in some configurations prohibits aircraft from landing on their preferred runway. For example, on the east side of the airspace, it is not possible to land on a more advantageous runway like one left if there is heavy demand for one right. As the use of arrival metering to Las Vegas is maturing, the FAA has started to expand its focus beyond ZLA and is developing an extended metering system with the adjacent centers, ZAB, ZOA, ZLC, and ZDV. This will allow any necessary delays to be absorbed over longer distances or on the ground, which is especially important at times with low Las Vegas arrival rate. While ZLA XM system is being developed, Los Angeles will continue to capitalize on a recent improvement delivered jointly by the FAA, industry, NATCA, and local community. Converging Runway Display Aid, or CRDA adaptation for 2-4 right and 2-5 left, and established on RNP, EOR, will provide a smoother sequencing for the RNP and straight-in traffic, and ability to execute simultaneous independent approaches. RNP procedures at Los Angeles allow curved path approaches for both arrival runways in either a west or east configuration. This recent operational improvement at Los Angeles has proven to be very successful from both an FAA workforce and industry perspective. The next steps include expanding the EOR authorization to east flow and the CRDA availability at other airports with curved approaches within the Southern California TRACON airspace. The transition to TBO is happening in large and small ways across the NAS. By addressing the needs of each operating area with the right tool at the right time, TBO incrementally improves overall NAS efficiency for the benefit of the aircraft operators and the flying public. Improving services through integrated data and technology means a safer, more efficient national airspace system for everyone. If you need additional resources to support greater understanding of TBO, we invite you to visit the TBO website at www.faa.gov/air_traffic/technology/TBO.